we've covered arc lengths in terms of its function here, s equals the integral from a to b, 1 plus the square of the derivative, dx, so the square root of that. Now that we've covered that, we've talked about that in the video, let's do some examples with the explicit functions. So I'm given a function here, and I'm given an interval here. So since I'm given an interval, I already know what a and b are. So I'm given a function, I'm not given its derivative. So the keys to doing this is we have to find the derivative, we have to square it, we have to add 1 to that value, and then we can go from there. But we have a formula, but we have to do some steps before we're ready to actually just shove our information into the formula. So let's write some on the board here. First thing is we're going to say that this is f of x. So I'm going to say f of x is 2/3 x squared plus 1 to the 3/2. So now what I need to do is I need to find f prime of x. So in this case I'm going to use the chain rule. Now I have something to a power, so what I do is I bring down the power, 3/2 times 2/3 x squared plus 1. Now 3/2 is like 1/2, so when we take 1 away from 1/2, we just have 1/2. But it's the chain rule, right? So we not only have to do the power rule here, we have to multiply by the derivative of that inside function. So that gives us 2x here. Now we're going to see that cancel. So I'm going to rewrite this. I'm going to rewrite this as 2x square root x squared plus 1. See, again, the 1/2 power, you can rewrite it as a square root. So we have f prime of x, but we don't have f prime of x squared. So let's square that. So when we square 2x, we're going to get 4x squared. And when we square this, we're actually going to get the absolute value of x squared plus 1, but that's all. X squared plus 1 is always positive, so it doesn't matter. So we're going to end up with x squared plus 1. So I'm going to rewrite this as 4x to the 4th plus 4x squared. That's how I prefer to write this. Now, what we want to do here is we finally need to add 1 to that, so I'm just going to add a 1 there instead of writing a new line. Hopefully you can follow along. Okay, so I have 4x to the 4th plus 4x squared plus 1. Now, I'm going to need to be a little more clever here. I can't just, if I try to plug this into that, right, specifically because I've got this square root I'm dealing with here. I mean, how in the world are you going to integrate that? So to do this, we need to be more algebraically clever. So what I'm going to do is I'm going to use there's a couple things I could do. I could do what we think of as a substitution, but it's not actually a substitution. You sort of have to trust me on that. Or we could think about the fact that hopefully in your algebra career, or maybe in your calculus career, you had to factor some powers that were greater than 2. So we could think of this as 4x squared plus 4x squared plus 1. So what am I thinking? What I'm really doing here is I'm saying this is 4 times something squared plus 4 times something plus another thing, right? So that's kind of this, it kind of looks like 4y squared plus 4y plus 1, right? That's that same form. So it's actually a quadratic form, but the powers aren't 2, 1, 0, they're 4, 2, 1. So in quadratic forms, what you are usually seeing is that you have a progression like 1, so you have 0 power, some power, and then double that power. So 0, 1, 2, you have 1 x squared, x to the 4th, right? So it's 1, some power, another power to the 4th. Another example of this might be if you had, 10z to the 6th plus 4z cubed plus 3, you could write that as 10z cubed squared plus 4z cubed plus 3. You'd have something squared plus that power cut in half plus a 0 power. That's the way that quadratic forms work. This is a very important concept. It comes up over and over and over. Okay, but that's an aside here. So we have this thing. We have a quadratic form, which means we can factor it. If I wanted to factor something like this, it would factor into 2y plus 1, 2y plus 1, which is the same as saying 2y plus 1 squared. Okay? Same thing here. This is going to become 2x squared plus 1, 2x squared plus 1, which is the square root of 2x squared plus 1 squared. So now we just have 2x squared plus 1 there. Now I know that's a lot to think about. There's a lot of writing here. I hope you were able to follow along. But we're going to finish this thing out. We're at the very end, honestly. So we now have this piece. It's that. So we just have to plug in the s. We just have to say s equals 0 to 2, 2x squared plus 1 dx. Thank goodness, right? Because that's a simple antiderivative. It's just 2/3 x cubed plus x from 0 to 2. Now, notice since these both have x's, the 0 will wipe it all out, so we actually only have to plug in the 2 here. So we end up with 2/3 times 8 plus 2. So that's 16/3 plus 6/3, so we have 22/3. So let me see if that matches what I'm supposed to get. It does. So 22/3. That's how we do that particular problem. Now, it's a bit of a doozy to kind of get off, but these problems are they can be kind of tricky. Arc length problems are not necessarily straightforward. You have to know your trig identities, you have to know your factoring. It's all stuff that you don't technically learn in calculus, but you probably forgotten before you got there. Good times, all right? So let's do number 2. F of x is natural log of sine of x. Now, one thing that's important to note here is that on our interval, pi over 4 to 3 pi over 4, sine is always positive. So we don't have an issue with the natural log here, right? We're in the domain. We don't have any problems. But it's always important to check. So that gives me that f prime of x. So we're going to use the chain rule again. The derivative of the natural log of something is 1 over the something times the derivative of that something. Well, the derivative of sine of x is cosine of x. And so rewriting cosine of x over sine of x, I can get that as cotangent of x. And this is going to be important because then when I do f prime of x squared, I get cotangent squared x. So then when I do 1 plus that, I get 1 plus cotangent squared x. Now why is that important? Well, if you remember your trig identities, 1 plus cotangent squared is equal to cosecant squared x. So then when I take the square root, I get the absolute value of cosecant x. Now, it's important. The reason why we do absolute value is because that is what it is. It's not just cosecant x. So let's look at this, though. We're on the interval pi over 4 to 3 pi over 4. So if you remember your unit circle, right, the unit circle can be broken into 4 quadrants. There's a mnemonic device that I learned 20-something years ago. All students take calculus. All trig functions are positive here. Only the sine function is positive here. Only the tangent function is positive here. Only the cosine function is positive here. So in pi over 4, which is this line, or that angle, and 3 pi over 4, which is that angle, the sine function is positive because everything's positive here. The sine function is positive because it's in the second quadrant. And the cosecant, remember, is just 1 over sine. So if sine is positive, 1 over sine is also positive. Why does that matter? Because that means that we don't have to antiderive cosecant of x, or absolute value of cosecant of x. We can just say cosecant of x. That's important. That's the kind of stuff that'll mess you up. If you do not pay attention to these small details, when you do certain problems that need an absolute value and you don't give it an absolute value, man, you will be beating your head against the wall, wondering why you're not getting it right. I'm telling you, these details matter. All right, let's keep moving. So now I have an integral from pi over 4 to 3 pi over 4 of cosecant of x dx. Okay? Now you probably don't remember this, but the antiderivative of cosecant is the natural log of cosecant x plus cotangent x. So that's going to go from pi over 4 to 3 pi over 4. So you may not remember your unit circle here either, and that's okay. So sine of pi over 4 is, so then we have to do the natural log of the absolute value of 1 over sine 3 pi over 4 plus 1 over tangent 3 pi over 4 minus the natural log of 1 over sine pi over 4 plus 1 over tangent pi over 4. So sine of 3 pi over 4 is 1 over the square root of 2. So sine of 3 pi over 4 is 1 over square root of 2. So 1 over that is just square root of 2. So you end up with natural log of square root of 2. Now tangent of 3 pi over 4 is negative 1. So 1 over that is still just negative 1. So you have square root of 2 minus 1 minus the natural log of, that's also going to be square root of 2. And that's going to be plus 1 because tangent of pi over 4 is also 1. So we have square root of 2 minus 1 minus this over here. At this point we can actually rewrite that as square root of 2 minus 1 over square root of 2 plus 1. So that's the natural log of that value. You know, at this point you probably plug in your calculator. At that point or that point, you could probably plug it into a calculator if you wanted to get it. If you want to keep going, you can multiply top and bottom by square root of 2 minus 1. So by the difference of squares formula, that's actually going to disappear. So because that's going to be 2 minus 1, so it's going to be over 1. So you end up with the natural log of square root of 2 minus 1 squared, which is 2 natural log square root of 2 minus 1. But something's wrong there. Something's wrong. Good deal. All right. This is a minus. Turns this into a minus. Turns this into a minus. Plus. Minus. Plus. Minus. Plus. Minus, plus, plus, plus. Disgusting, right? Like, I apologize. That's a big oversight on my part. How did I know that? Well, I knew that because the square root of 2 minus 1 is actually less than 1. And the natural log of something less than 1 is a negative value. and the natural log can't, or if the arc length was a negative value, that wouldn't make sense for what we're doing. So I knew that something had to be off. My antiderivative was off. I never antiderive cosecant of x, so I apologize for that. But anyway, it's always good to have these little accountability things. They help keep you sharper.